and today we'll be discussing groundwater recharge, right? Okay, just for an introduction, note that most of natural groundwater recharge comes from rainfall or precipitation. And what happens is we have to determine first which proportion of precipitation is actually available for groundwater recharge. After we take into account how much water is lost to overland flow or runoff, and how much is also lost to evapotranspiration. Right now, we have to discuss these two processes in order to properly understand how much precipitation is actually left for groundwater recharge. And now for runoff, the key factors for understanding how much runoff we will have from a given precipitation is the soil type, and then the antecedent or the pre-existing soil moisture, and then also the land cover, like is it an urban area, is the watershed forested, and so on. Right now for soils, in general, your well-drained soils like sands and gravels have high effective porosities and high hydraulic conductivities, meaning they are able to transmit water fast, and they're also able to store a lot of water. And then land cover will actually tell you how much fraction of precipitation is available for infiltration, like particularly how much of the ground surface is actually exposed or is open for infiltration. For example, if you're talking about an urban area with concrete or asphalt surface, you can expect uh more or less a surface that can barely allow infiltration. On the other hand, if you're talking about a forest, right, with all those roots and more or less soil that is open for infiltration, okay, so you can expect a lot of infiltration in a forested area. Okay. Now note that all the available rainfall will infiltrate the subsurface until the rate of precipitation exceeds your infiltration capacity. Okay, so at which point ponding and subsequent runoff will occur. Now this just means that your infiltration rate can only go as can only go fast. Okay, it has a limit. Okay, if your rainfall, if you're bringing in more water from rainfall faster than the actual infiltration, what will happen is you will start to have excess water on the surface, and they will just result in ponding. And eventually, when you have a lot of ponded water and still have a lot of water coming in from the rain, they will eventually turn into runoff and flow over your land. Okay. Now, this is a chart that shows the relationship between your infiltration and the time, okay, from the start of your infiltration. Your y-axis is showing the infiltration rate, so higher is more infiltration, and then your x-axis is the time elapsed in this is on a logarithmic scale. Okay, and we also have three precipitation rates here. The solid line is representing 0.008 centimeters per second of rainfall, and then you have a small dashed line here which shows 0.004 centimeters per second, and then you have a straight line here which represents 0.001 centimeters per second, and finally you have a slightly bigger dash which represents 0.0008 centimeters per second. All right, note that this plot is taken from a soil column which has a soil with a saturated hydraulic conductivity of about 0.001 centimeters per second. Now let's talk about the first precipitation, which is the 0.008 centimeters per second. Right, as you can see here, we have a steady infiltration rate of 0.008 centimeters per second, which matches your precipitation rate. And it continues until time is equal to around 600 seconds. Now what's happening here is you have your rainfall that is that's just spreading out and infiltrating and being stored inside the pores of your soil column. Okay, so the spreading of the rainfall and the storage is showing a rather fast infiltration rate until it eventually reaches its until the soil gets fully saturated. Okay, once the soil gets fully saturated, it means that it doesn't have any more soil pore spaces for storage. Okay, and the infiltration rate will now be limited by the saturated hydraulic conductivity of your soil. And from that point, we start to have a ponding, meaning the water is starting to accumulate on the surface, and the infiltration eventually drops here and asymptotically reaches the saturated hydraulic conductivity of the soil. Okay, so just to summarize, at the start, okay, uh, at the start of your rainfall, the infiltration rate will be dictated by your precipitation rate. Okay, that's because the rain can spread out. It can be stored by the soil, and once the soil is fully saturated, okay, you get ponding, you get all the pores filled up with water. At that point, the saturated hydraulic conductivity will control the rate of infiltration. Okay. Yeah, so you have similar stories for other precipitation rates here. Okay, like for 0.004, you started 0.004 infiltration rate, and then you get ponding and it drops off. And then for the smaller precipitation rates, you have a different story. So they just follow the precipitation rate and the set for 0.001, since your rainfall is just the same as your saturated hydraulic conductivity. Okay, you essentially have a flat response here. Okay, and same for for the small precipitation rate of 0.008. Now let's talk about the method for calculating runoff given a certain number of precipitation. I think in the exercise I showed a different method, which is the rational method, okay, which is a much more simpler method compared to the soil conservation service runoff curve number. I am emphasizing this method because if you are seriously looking into hydro hydrological and hydrogeological studies, you have to be familiar with this method because this is what is used in most of the hydrological and hydrogeological studies, like heck HMS. Right now, the SCSCN involves determining runoff as per the influence of precipitation and the infiltration characteristics of your soil type, or infiltration characteristics as per your soil type, your soil moisture, your previous rainfall, your cover type or the land use, okay, and the surface retention or how much water is being held back by your soil. And then the method also includes how to calculate the peak discharge, all right, for a given stream or for a given watershed. So you can actually determine how much the stream flow will spike, okay, for a given rainfall. So this is important if you're doing flood studies, okay, or because in flood studies the flood occurs once the stream flow or the river flow spikes, okay. But for this lecture, I won't be discussing how to calculate the peak discharge, okay. I'm just dropping off that you can determine the peak discharge from the SESCN. Okay, so let's just focus for now on the infiltration uh, component, okay, and the runoff of the SESCN method. Okay. Now, the start of the method is you have a mass or a volume of rainfall that is converted into runoff using the curve number. You have Q or runoff is equal to precipitation minus your initial abstraction. Okay, and that quantity is squared, and then you have your quantity of precipitation minus initial abstraction plus your potential maximum retention after your runoff begins. Okay, so what is initial abstraction? This is all the losses that occurs before your runoff begins. This includes the water that is stored in your surface depressions, like your potholes in your road or your carabao ponds in your farms, and also the water intercepted by vegetation, evaporation, and infiltration. So this number represents all the number that is captured at the start. Okay, it's captured and stored. So the keyword here is the losses. So this is all the water that is quote unquote lost before your runoff. Okay. Now note that initial abstraction is highly variable, but this is typically correlated with soil and land cover parameters. And from the studies of many small agricultural watersheds, IA was found to be approximated by IA is equal to zero point 0.2 multiplied by S. Now, if you plug this equation into the previous equation, you get Q is equal to P minus zero point 0.2 times S, and that quantity is squared, and then divided by P plus zero point 0.8 times S. Right? Now, now let's talk about the maximum water retention, okay, which is part of the SCS equation. Maximum water equation includes your infiltration, interception by vegetation, evapotranspiration, and storage. Okay, so this is the water that is being continuously lost, okay, to different storages and interceptions. Okay, as your rainfall progresses. So the difference between initial abstraction and water retention is that initial abstraction only occurs at the start. Okay, after that after you have filled up your initial abstraction, okay, you stop lose okay, you stop feeding water into the initial abstraction. Okay, once it is filled up, you don't care about initial abstraction anymore. For water retention, this is more or less a continuing rate of water being lost to different processes, especially your evapotranspiration. Okay, so you're continuously losing or bleeding water due to water retention. Okay, and this number is given by S is equal to 1000 divided by your curve number minus 10. And you can have different values for curve number for watersheds, and it ranges from 0 to 100, where 100 is perfectly impervious. You can imagine this as for example, a surface that's covered by tarpaulin or covered by a perfectly sealed asphalt or perfectly sealed concrete. And this is the guide on how to get your curve numbers. Okay, you have a table here, and you have your columns, right, denote different cover or land use types. You have your pasture, grasslands, and then you also have your continuous grass, and then brush or weeds. Weeds like the literal weeds, and bushes. So brushes are just essentially bushes. And then you have your woods and grass combination, and then finally have your woods. Okay, notice that as you go from pasture to woods, you are getting a smaller and smaller curve number from 68 to 30. Okay, so the smaller the number of your curve number, the more water you are actually the more water you have available for infiltration. And the higher the curve number, the more runoff you have for overland flow. Okay, so you can just see curve number as more or less a good representation of how much runoff you can get from your rainfall. Now your columns, okay, so you have your columns here, you have A, B, and C, and D. These columns represent your soil type, your soil groups, okay, which are as per the USDA soil texture. Right? Note that USDA soil texture is different from your USCS soil texture. Although you can convert them, okay, it's possible to convert USDA soil texture into USCS. So, though it's an imperfect conversion. So soil group A is sand and your sandy soils. Soil group B is your silty loams. Soil group C is your mixtures of clay, and then soil group D is your clay soils. Okay, note again that as you go from sandy soils to clay soils, you have a progressively increasing curve number value. Okay, this means that clay soils, okay, since clay soils are impervious, you don't get a lot of infiltration when you have clay soils. So you can get a lot of runoff when you have clay soils in your site. Right now, this is just a chart that shows your direct runoff in your y-axis and then your rainfall in your x-axis. And we have different plots of curve numbers, okay, from 100 to 40. Okay, and you can see here that for curve number is equal to 100, meaning you have a perfectly impervious surface. You essentially have a 1:1 correspondence between your rainfall and your direct runoff. Okay, so 1 inch rainfall corresponds to 1 inch of runoff, and so on. Okay, so it means that you have a 100% conversion of rainfall into runoff. Now, let me just clarify here. Why are we measuring rainfall and runoff in inches? Okay. We use inches, or we just use a one-dimensional number for precipitation and runoff here. Okay, because uh, this is supposed to be multiplied by your watershed area. Okay, if you want to calculate the actual volume. Okay, so if you have a watershed that has a 1 million square inch of area, you just multiply that by the rainfall in inches to get the volume of your rainfall. And the same happens here. If you have 3 inches of direct runoff, just multiply that by the area of your watershed to get the volume of your runoff. Anyway, going back. Now let's look at curve number is equal to 40. Note here that you hardly get any runoff at the start. Okay, so the runoff at curve number is equal to 40 starts at around 3.5 of precipitation. That means that you are just initially abstracting water from the rainfall until you get 3.5 inches of rainfall. At that point, the soil or the soil storage or the storage areas in your site has been filled. Okay, and that's only the point where you start having overland, where you start having runoff. All right. All right. Now for practical reasons, if you're intending to do hydrologic studies, like for your thesis or for your project, note that since the SCSCN method is heavily dependent on soil type and land use, okay, I'm showing you some sources where you can find your data. So soil maps can be found in the Bureau of Soils and Water Management, or you can actually access the PhilGIS website given in the link below. Now, the cover type. Okay, for the cover type, you can either manually classify your satellite imagery, like manually trace out outlines in Google Earth and label the land use of that area, or you can also do an automated classification like in GrassGIS or NV using Landsat datasets. All right. Now let's talk about evapotranspiration. All right, sorry. Let's talk about evapotranspiration. Now, evapotranspiration is just your evaporation from your land plus your evapotranspiration plus your transpiration from your plants. As shown here on your first animated GIF, we can see here, okay, you can see some evaporation of water from your soil, and you also get transpiration from your plants. Okay, you can even zoom in your plants and you can see how your water molecules are being transferred out from your plants. Now, in terms of water budget, evapotranspiration is the second largest component of your water budget, only next to your precipitation. And note that for all the precipitation that falls on land, 65% of it returns to your atmosphere through evapotranspiration. Okay, so the rest goes to your ocean and then also undergoes evaporation. And typically, your evapotranspiration is expressed in inches per day or millimeters per day as per your meteorological data, which we'll be discussing later. Right? Now, let's talk about potential evapotranspiration. This is just about evaporation only. So, it's kind of misnomer. Okay, so it only talks about evaporation, and this talks about the maximum possible evaporation given an open water surface. Okay, this is typically used for your irrigation optimization studies, where you want to make sure that your irrigation water is not lost to evaporation. So you have to know how much is your potential evaporation. So I think this is tackled in the first exercise. Now another or rather the more important thing we have for evapotranspiration is the reference crop evapotranspiration, which is also called the reference evapotranspiration. This is just the rate of evaporation from an idealized grass crop with a fixed crop height of 0.12 meters and an albedo or reflectivity of 0.23, a surface resistance of 69 seconds 69 seconds per meter. Okay, so this is what we typically use for our evapotranspiration inputs in our water budget. And for this part, I will be discussing two methods for getting evapotranspiration. The first method is the Penman-Monteith Evapotranspiration, or the FAO-56 method. This is the most widely used method for calculating evapotranspiration, and we have the details of the document and the provided link if you want to study it further. But for now, let's just gloss over the method. So this method accounts for reference evapotranspiration, temperature, solar radiation, wind speed, and atmospheric pressure. And you can actually calculate this even if you don't have an on-site meteorological data. Sorry. And if you're and actually this method involves like 5 pages of equations. So it's actually more practical to use a program like CropWatt to calculate evapotranspiration using this method. The other method is your pan evapotranspiration method. This is a much more simpler one, and you only use a what you need here is just a set of water-filled pans. Okay, and the common one is the Colorado sunken pan type of evaporation pan. And it's quite simple, so you just need to know your pan coefficient or K sub P. Okay, so your pan coefficient, sorry, and then you just multiply it by your pan evaporation as measured by your evaporation pan. Now the value of K sub P ranges from 0.35 to 0.85. Okay, so there are factors considered there, but for our purposes, we don't need to go further into that. Okay. Now this is just a picture of a Colorado evaporation pan. So you have your water in here. You have water. You have your pan, and then you have a measuring. You have your instrument here. Yeah, sorry for my crappy handwriting. And you also have your wind speed. Okay. Alright, so that more or less is your evaporation pan. And if you actually need this data, you can go to Pag-asa. Okay, Pag-asa has a record of their evaporation rates. Okay. Now let's talk about the vadose zone or the infiltration in the vadose zone. Okay, so far we've talked about the more or less the surface processes like your runoff and your near surface storage. And now we have just talked about the evapotranspiration. So if you can do the if you know how much water is left for infiltration after you've calculated your runoff and evapotranspiration, you now know how much water is left for infiltration in the vadose zone. Okay. Now let's just discuss now how. So the discussion here will focus on how fast infiltration occurs. Okay, in the vadose zone. So the process here is that you have your water from the surface, and then you have your precipitation, and then you have your water table, and then you have your this zone is your vadose zone, and then this zone is your groundwater. So note that some water is lost to runoff. Yeah, that's runoff, man. Not so that so you lose some precipitation to runoff, and then you also lose some water to evapotranspiration. and then the water left there is you have some water left for infiltration. Okay, and that involves passing through your vadose zone. Now, your vadose zone is it's kind of a special child with special properties because in the vadose zone you have a lot of factors that slow down your movement of water. Okay, so it's a freaking fucking slow process. Okay, which we will be discussing later. Right, so there's a lot of stuff that slows down the movement of water in your vadose zone. And but once it reaches your groundwater, you more or less have a fast transmission of water here. Now, what is vadose zone? As discussed, this is your soil above your water table, hence it's not saturated. Okay, saturation means if you have a soil that is saturated, that means that all of its pore spaces have water. In the vadose zone, it's not. Okay, your vadose zone, your pore spaces have air, and some of them have water, some have air. But the point is, vadose zone is a non-saturated zone, and this is where infiltration occurs. Okay? And it involves a slow movement of water compared to your groundwater. Again, infiltration is a function, or the speed of your infiltration is a function of your soil layers properties. And this is one important principle in hydrogeology that you have to remember. When you have a layer of soil, right? So let's say this is sand. And then this is, let's say, clay. And then again, you have sand. Okay. So let's say you have your rainfall here, and it goes through your sand, then to your clay, and then your sand. Note that the rate of transmission of water is very very fast in your sand layers, but very very slow in your clay layers. Okay. But note here that so you have water here starting from the surface. It travels fast through your sand, okay, and then it encounters your clay layer. Okay. So it actually spends a lot of time passing through your clay layer here, okay, before it reaches your sand. So note that uh, typically the slowest and the uppermost layer dictates or dominates the transmission rate of water. Okay, when you have a layer, what dominates here is normally the slowest layer that you have. So even a thin layer can greatly slow your infiltration rate. And another thing with infiltration or with unsaturated soils, all right, unsaturated soils have a very slow infiltration rate, but this one speeds up as you increase your saturation percent. Okay, so the more water you have in your soil, paradoxically, you get faster infiltration. Okay, All right, so now once all the soils are saturated, your infiltration reaches its maximum. So it reaches your saturated hydraulic conductivity. So now don't confuse this with the earlier chart I showed you. So I think I showed you a chart showing the curve, the infiltration rate, right? As modeled in the SCS, SCSCN method. So in the SCSCN method, what makes your initial infiltration fast is the storage and the spreading out of your precipitation. Okay? Now, when you're talking about your vadose zone or the subsurface, what happens is you start with a slow infiltration rate and then it eventually speeds up as it reaches its saturated hydraulic, its full saturation. Okay? Once you get full saturation, you get your maximum infiltration rate. And now, but if you still have a precipitation rate that is bigger than your infiltration rate, you will eventually get ponding and then runoff will start. Okay. Now let's talk about one of the other factors that slow down the movement of water in your vadose zone or in your unsaturated soil. This is what we call the matrix potential. And it has different names. Okay, it's like a demon or a fugitive. It's also called water suction. It's also called capillary potential. It also goes by the name of capillary pressure head, suction head, metric pressure head, tension, and pressure potential. Okay, so it has one, two, three, four, five, six. Okay, it has seven fucking names. Okay, actually eight if you include metric potential. It has eight different names for a single process. Okay. Now, what metric potential does, it exerts an upward suction effect on water. So it pulls up any water that you have on your soil. So it has a pulling effect, and this comes from the capillary and adhesive forces caused by the air in your pore spaces. So what is capillary action? Let's review. So capillary action is all about the surface tension of your water. Alright, so water has water technically loves to pull. Okay, just imagine that water loves to pull each other. Okay, so if you can imagine you're a water droplet, so let's imagine a water droplet, and then you introduce a water droplet here. What happens? It will suck up this smaller droplet, and they will merge, and will form a bigger droplet. So that is partly caused by surface tension. Okay, so water loves to pull each other. Okay, so if so, what happens is your water on the upper areas tend to pull up the other water from the lower elevations. Okay, so that's how capillary forces work. And then you have adhesive forces, which involve your attraction between your water and soil. All right. Okay, so note that matrix potential only occurs in unsaturated soil, so it only occurs above the water table. It is a negative pressure, meaning it literally sucks. Okay, it literally sucks, and so since it pulls up your water and water loves to actually wants to go down, it actually slows down the movement of your water. And that results in a low hydraulic conductivity in your soil when you have unsaturated conditions. Alright? But now note that as you actually increase your water content, okay, you get less air with pore spaces, okay, and you in effect you reduce the capillary and adhesive forces. So you actually lose your matrix potential when you have full saturation. Okay, at full saturation you have zero matrix potential, and in effect you get faster hydraulic conductivity. Okay, it becomes fast. All right. Now, matrix potential also varies from soil to soil. This, the rule here is the more or the smaller your grain sizes are, the more surface area you have, the more matrix potential you get. Okay. Right now, this is just an illustration of how your matrix potential or your suction head, as shown in your y-axis, varies with your saturation. So you have here saturation in your x-axis. So this is 100%. So one is 100% saturation. Note here, you have two different types of soils, fine sand and coarse sand. And at 100% saturation, you get zero. You get zero suction head. Okay. And when you have saturation that is less than 100%, you get increasingly negative. You get an increasingly negative suction head. So these are negative values, all right, because they are sucking. Okay. Okay. Negative pressure sucks. Positive pressure exerts pressure. Okay. Now let's go here. And we can definitely two different patterns with your fine sand versus your coarse sand. All right. For your fine sand, you definitely have bigger values or more negative values of suction head compared to your coarse sand. Let's say, for example, at saturation equal to 50%, you are getting like approximately negative 25 uh, centimeters of suction head for your coarse sand, and you are while for your fine sand you are getting approximately negative 120. Okay, so that shows how the grain size influences your matrix potential. Okay, finer grains mean larger surface area of your soils, and you get more matrix potential. Now let's talk about factors which affect your groundwater recharge. All right, so first is your climate. Of course, it's quite obvious. The cooler and the wetter the climates are, the less transpiration you get. Okay, cool climates have less evapotranspiration, and wet climates have more precipitation. So when you have more precipitation and less evapotranspiration, less ET, more precipitation, you get more recharge. And another thing here is that mountain microclimates or high elevation areas receive more precipitation than your low-lying areas. Okay, so I think this is easily observed if you travel to Baguio or Sagada. You are essentially getting rainfall like every 3 p.m., every 2 p.m. Okay, so you get a lot of water in your mountains, and they actually contribute a lot of recharge to your low-lying areas. Okay, so if you're studying groundwater recharge and you have a basin, don't forget or don't just discount the contribution of your mountain areas to your low-lying areas. Okay, because mountain areas contribute a lot of water to your recharge in these low-lying areas. I mean, for Metro Manila, we are probably relying a lot of recharge from Rizal and Bulacan areas. Now, another factor for recharge is your geology and topography. All right, as discussed before, soils. Okay, it depends on the soil you have. If you have a thin layer of permeable soils like sand and gravel, they are conducive for recharge. But if you have a thick layer of clay, that will essentially block water from reaching your deeper surfaces. And then if you're talking about rocks, uh, vertical beddings, vertical fractures, vertical faults have the highest recharge rates. And then if you're talking about your karst or your limestone areas, the mature karst or the areas with lots of sinks and sinkholes have the highest recharge. And then for topography, typically the gentle and flat-lying slopes are the most conducive for ponding infiltration and therefore also recharge. And then also mountains, okay, create precipitation shadows on the leeward side. So this just to illustrate, if your wind is going this way and you have a mountain here, what happens is you get an accumulation of clouds, or you get most of your rains being forced to pour on this side. Okay, so if your rain or clouds are going from this direction and you have a mountain here, what happens is the mountain acts as a big ass barrier that forces your moisture in your air to precipitate on this side. And as a result, it deprives the leeward side of precipitation. You get a shadow. Okay. This is what's happening in the Ilocos area. So in the Ilocos, you have your cloud masses going in from the Pacific are actually being intercepted by your Cordillera mountain range. All right, and as a result, Ilocos is mostly deprived of rainfall. Okay, so you have a rain shadow in Ilocos, and this is your Cordillera. Okay. Another factor is land cover and land use. Note that urbanization involves impervious surfaces such as concrete and asphalt, which decreases infiltration and therefore it decreases recharge. The story is slightly different for forests that are converted into agricultural lands. because you are, in a sense, you're increasing recharge through your irrigation. Although the downside of irrigation is that most of the time irrigation is also just what it's just irrigation from your groundwater. So you're essentially just cycling back your water from your groundwater back to your agriculture and then to your groundwater again. So in a sense, when you have agricultural lands, you can get more recharge due to irrigation, although you are increasing the extraction of groundwater. So then the net increase in recharge by might be actually small or even negative in agricultural areas. All right, now let's talk about how do we estimate groundwater recharge. Okay, so this is a very, very difficult study to do, and there are various methods that we can use. One of them is your lysimeters. All right, you can imagine lysimeters as it's like a subsurface rain gauge, except that you are measuring infiltration. So this is a lysimeter, and what we do is we bury it to the subsurface, and then it catches water, and it can measure the infiltration rate in the subsurface. And note that infiltration is not equal to recharge. Okay, not all water that is infiltrating into the VDOS zone will actually reach your groundwater. Some of them, some of the water infiltrated into the VDOS zone just can exit can exit the VDOS zone as stream flow. Okay, and the value of lysimeters is that it can be used to calibrate empirical equations or numerical models. And this is actually the only method that is capable of conducting direct measurements of infiltration in the VDOS zone. Although the downside is it's very expensive and it cannot monitor deep aquifers that are greater than 3 meters. Another method is soil moisture measurements. Okay, so what you do is you measure your matrix potential and then you measure your soil moisture. And from there, you can eventually derive the unsaturated hydraulic conductivity, which can then be used to model your recharge. Okay, and the other method, and this I think is the most one of the most important method, is the water table fluctuation. This involves studying the rise in water table after a big rainfall event. Okay, what happens is, or rather, sorry, this is actually the most commonly used method for humid regions like of course your Philippines or India. And I think the only limit of this method is that it depends a lot on the value of specific yield. Specific yield, it's a number which tells you how much water can you get, how much percent of water you can extract from a given volume of your aquifer. Okay. We will be discussing specific yield later on this course. Okay, but for now, just you just have to know that specific yield is all about how much water can be extracted from from a given volume of of an aquifer. All right. And another limiting thing in water table fluctuation method is that you have to measure your water table at least once a week or more, or more frequent if you can. All right. The details of the water table fluctuation method is discussed, I think, in exercise 2 or 3. So I won't be discussing the details of it for now. But now let's move on to the other variant of water table fluctuation method. We have here the double water table fluctuation method, which is actually more accurate than the its single brother, because double water table fluctuation method allows you to calculate both recharge and specific yield. Okay. Note that these two variables are one of the hardest, are notoriously difficult to measure. Okay, they are very difficult to measure. Sorry, that's supposed to be a skull. Okay, they are very difficult to measure, and this method allows for accurate estimation of those two variables, which is, I think, which is actually very valuable. And what happens in this method is we divide the year into 2 seasons. We divide them into wet and dry seasons. And then we apply water table fluctuation method twice. Okay? So what happens is we plug in values into this equation. Sorry. What happens here is we have this system of two equations. All right? And we don't know recharge, we don't know specific yield. Okay? We don't know these two numbers. And so we don't know these two numbers, and what we have to do is we just need to do the water table fluctuation method to get numbers for your RF, which is your irrigation return flow, and then your inflow from water inflow into your basin. So RF, or water irrigation return flow, is just the water, or the irrigation water that is returned to your aquifers. And then your E is your evaporation or evapotranspiration. PG is your groundwater extraction lost to pumping. And then Q out is the water you lose to is the water inflow that is lost that is going out of your watershed. And then the SY times delta H is the water you are either losing, that is being lost or being gained, as indicated by the change in your water table. Okay, so if you would look at this system of equation, this is just a pattern showing you the left side are just variables that are describing the inflow of water into the basin, and the right side is describing parameters that indicate outflow of water from your watershed or from your basin. Okay. Now let's talk about environmental tracers. All right. Environmental tracers are this method actually allows for determining, all right, the recharge rates in an aquifer. Okay. So you actually have to be aware that aquifers involves a very, very wide time scale, like ranging from days to thousands of years. I mean, in a practical sense, some water, all right, in a given aquifer, like for example, water that is 100 meters deep in an aquifer, it's possible that some of them came from precipitation that occurred like thousands of years ago. All right, so this is important to know when you are doing long-term sustainability studies. Like for example, when there are instances where I think I encountered this in New Zealand. They have deep wells which are extracting water, of course, deep into the ground. And then upon studying the ages of the groundwater that they were extracting, they found out that those water are actually thousands of years old already. Okay, so what's the practical implication of this? I mean, who cares if the water is 1,000 years old? Well, the practical implication is that it means that it took a fucking long time for that groundwater to reach that depth. Okay, and it means that you are probably looking at thousands of years before that groundwater is actually replenished. Okay, so it's really ideal to avoid extracting water from really, really old aquifers because they take a lot of time to replenish and you might be depleting them, okay, by getting water from them. I mean, the term is mining water from them. All right, now, environmental tracers are actually also useful in arid environments where you have low recharge. And tracer concentrations are actually very precise compared to other recharge methods that you can use in an arid environment. Now, the tracers that you use will depend on the ages that you are anticipating. If you are anticipating aquifers that are less than 50 to 70 years old, then you can use fluorocarbons or CFCs, or you can use the ratio of tritium and helium. Okay. Now, if you're dealing with much older water, you can use carbon 14, oxygen 18, deuterium, and then chlorine 36. Now, the general idea of using isotopes is basically you have to note that precipitation or meteoric waters or surface waters are abundant with isotopes such as oxygen or contaminants such as CFC. And note that, all right, and we can actually establish the initial concentrations of these isotopes on the surface. And note that isotopes transform into their more stable ones over time. Okay, so they break down radioactively into more stable isotopes. And over time, all right, water eventually gets lower concentrations of these unstable isotopes. So as your water goes down to your deep aquifers, they start to lose, or they start to wean off their unstable isotopes. Okay? So if we can establish how much unstable isotopes are present in a given water, and we can and if we can compare it to the well-established concentrations or baseline concentrations, we can use that to accurately estimate the numerical ages of your water. So the idea is the decay of isotopes is more or less well known. I mean, we have a concept of our half-life. Okay, half-life is the number of years it takes for a given isotope sample to to decrease by 50%. Okay, so we know how fast it is decaying. So if we can take a sample from your old aquifer and compare its isotope concentrations to your surface water, we will be able to know how much time has passed. Okay, all right, and we can determine the age of that water. So this is an example of an aquifer, okay, that is dated using CFC. All right, and then basically from the CFC they were able to determine that the water at about what's this? At about 30 feet below the ground surface is the water that originated from a precipitation in 1985. And then as you go deeper and deeper, you have a progressively older water. So how that works is we just take the reference year here. So this study was done in 1990, and at 1, 2, 3, at approximately 120 feet, we have water that is approximately 30 years old. All right, so it took 30 years, all right, for the whole hydrogeologic system to recharge the water at this depth. Okay, so this water is very difficult to replenish because it takes approximately 30 years to replenish that stock of water. And then the other method for estimating recharge is the base flow separation method. And it's important to note that stream flow or river flow, okay, because this method is applied on a river flow or a stream flow. So a stream flow is actually an aggregation of water from different sources. So river water or stream water is composed of one, your direct precipitation over the surface stream, meaning the water that is directly landing on on your river. Number two is surface runoff collected by the stream, meaning the water that is coming from the surface and draining into your river or your stream. Number three is near surface flow of newly infiltrated water. So this is water that has infiltrated into the vadose zone but was not able to reach the groundwater. So what happened is your water in the reduced zone, uh, it went to your reduced zone. Sorry. So you have here your water table. This is your groundwater. This is your reduced zone. So what happened is your water actually infiltrated into your reduced zone, but it did not reach your groundwater, and it was diverted into your stream. All right. So that is your underflow or your near surface flow. And then you also have your groundwater flow, which happens if you have a deep river, and your groundwater is actually contributing to to that stream. Now, for practical purposes, it's easier to just lump together all these three. To just lump together your direct precipitation, your surface runoff, and your underflow, and assume that they are just part of the surface runoff. Okay, so in effect, the method is just about separating surface runoff from your groundwater or from your base flow. And further, we assume that the groundwater inflow that is coming into the streams are coming only from your groundwater recharge, and therefore groundwater stream inflow is equal to your groundwater recharge. Okay? So if you can measure or all the stream flows in your watershed, so if you have a watershed here, and this is your stream network, all right, you have different rivers. So if you do base flow separation, if you do base flow separation in all those in all these three streams, oh sorry, in all these 1, 2, 3, 4, 5, 6, 7. I mean, sorry. So let's say you have this river. All right, so you have this watershed in this river network. If we can do a base flow separation method at the mouth of the river, all right, we can essentially determine the total groundwater recharge for this whole basin. All right, because this main river is the ultimate outlet of this watershed. Now, there are limitations for this method, so you can't use this in karst terrain. Okay, you can't use this on a non-permanent stream. It's also not useful in a riparian vegetation or a highly vegetated floodplain. Or if you are dealing with a river that is taking recharge from deep aquifers. This is especially applicable for aquifers that are getting a lot of recharge from your mountain areas. And you also can't use it on an area that is heavily influenced by a dam. All right. Now, the steps of your base flow method is as follows. So you take a hydrograph. So a hydrograph is just a plot of your stream discharge versus time. for a particular rainfall event, such as a storm. Okay, the most ideal is like a storm. And then you select a method depending on your situation. If your streams is getting a lot of groundwater inflow, you use the ABC method. If you're not getting a lot of water inflow, you can use the ABD method. And then the step 3 is you just delineate the boundary between your base flow and your surface runoff. Right, let's discuss the ABC method. So this is your hydrograph. Okay, this black line is a plot of your discharge versus time. Alright? So this part is your normal stream flow, and then this part is where your rainfall event starts to influence your rainfall event starts to influence your stream. So the discharge spikes. Okay? It goes very high, and eventually it wanes down until it reaches its normal stream flow levels. So in the ABC method, we have 3 points. So we have A, B, and C. A is the inflection point at the onset of the surface runoff. So this is the start of your rise in your discharge. So the moment your stream discharge goes starts to rise, that is your point A. And then point B is just your is the location of your peak discharge. And then you can just draw a vertical line. All right. And point B is somewhere in that area. So let's skip point B for now. Let's go to point C. Point C is just is taken by doing a straight line trace of your river flow. So you just look for the straight line part. So this is the straight line part. All right, this is more or less the straight line part. And what we do is we extrapolate this line until we reach point B. So should be approximately here. All right, and point C is the point of tangency. All right. Now, once we have all these 3 points, A, B, and C, all we have to do is just connect the dots. And that is the boundary between your base flow and your runoff. So this is your base flow. This is your runoff. All right. So this part is basically your groundwater. This part is basically your surface water. Now, the other method is your ABD method. So we have 3 points here, A, B, and D. And as before, A is the inflection point or the start of the increase in your discharge. So that is A. And then B again is the point of your peak discharge. So this is your peak. You just draw a vertical line down. And then D is the location. So you have to compute this location. Okay. So what we do is we start with point B and then we add N, where N is equal to 0.8 times your drainage area in square meters raised to to point 2. So if your drainage area is, let's say your drainage area is equal to 10 square kilometers. Let's compute that. 10 square kilometers. 10 square kilometers raised to 0.02 times zero point 0.8 is approximately 1.2, 1.27. So that is expressed in days. Okay, so you just add this number to this part. So I just add the position of B, add add n to the position of B, and you will get the location of D. Okay, and from there you just have to connect A to D here. Sorry, so this is just an AD method. Okay, my bad, my bad. So this method only involves A and D. All right. So after that, so just connect A and B, A and D. So after that, this is your boundary between your base flow and your surface runoff. Okay, so this is your surface runoff. This is your base flow. All right. So that ends this lecture. All right. Thanks for listening.